one. So what do we have here? We have the bipolar transistor that we had, I think, in 4.10. It had a microphone with a small input. And that was riding on top of a voltage source that made this base emitter forward bias. Okay, and then we had a resistor this time with a value of 100 ohms. And we had a VCE of 1.8 volts. Let's see.
What are the subscripts for V? Is it VREC?
Oh, sorry. Boy. I should have been a medical doctor with my writing ability. It's just VBE. Is 800 millivolts. Is that the one you mean?
Yes.
Okay. So VBE is 800 millivolts to turn this guy on, and VCE is 1.8 volts. And from 4.10, sorry, we had calculated, so you have to refer back to that. We had calculated I sub C is equal to 6.92 milliamps. Okay, so the first question is verify that Q1 is in forward active mode, is in forward active. So basically, the question comes down to, we got two requirements for Q1 being in forward active. This base emitter junction needs to be forward bias. Okay, that 800 millivolts should do it. Get that forward bias. And the second condition, which we'll have to check, is that this collector, the collector base junction is reverse bias. Okay, so that's what we got to do right now to just verify that it's in forward active. So we know what this, we've been told what this current is from 4.10. This I sub C is equal to 6.92 milliamps. So we can just calculate this voltage X, and it's just VCE, so the voltage, what the heck? V of X is equal to VCE minus I sub C times R sub C. Okay, it's 1.8 volts minus 6.92 times 10 to the minus 3 amps times 100 ohms. So what is that? So this comes out to 0.692 volts, I believe. I trust myself. Yep. And so this number ends up being 1.108 volts. Okay, so that's this voltage at X is 1.108 volts. So the question is this put the base or the collector base junction in reverse bias? And it does, because the base voltage is at 800 millivolts. This guy, the collector, is at 1.108. So we have about 300 millivolts of reverse bias. So we have, so yes, Q1 is in forward active. Does anybody have a question about that?
No, so basically you just said that, Vx is just the voltage of VCE minus, the voltage dissipated on the resistor, right?
Yep. So you're just confirming that it's in forward active mode. That's a really important thing to do as we get into chapter 5, because you get sort of wound up designing your gain stages and you forget to double check your bias conditions to make sure you're good. So this is always a good idea once you're done designing your gains, et cetera, to go back and make sure your bias condition is correct. Okay, so go ahead, sir.
And then this is bigger than VB. This is why it's forward bias, right?
It's bigger than VB. Yeah, exactly.
Okay, thank you.
Yeah. So the second question is, part B is, we're supposed to figure out, so we want to determine output signal level. If input is 1 millivolt. Okay, so let's visualize this to begin with. Okay, so because I know this concept of bias and small signal gain and stuff are kind of hard to get your head around. So this is what it's asking. Okay, this is what we've got. So we've got this plot of VBE versus I sub C. Okay, and we're told that the bias condition that we're on from exercise 4.10, from example 4.10, we're told that we are centered at VBE. Well, we know that just because we have the circuit, right? Our VBE is 800 millivolts, and that gives us an I sub C at 6.92. So we're centered around there. Boy, I did that badly. Whoops. Hello. Boy, I tell you guys, it's one of those days. Even my pen doesn't write here. So 6.92 milliamps. Okay. So that's where we're centered. And then it's saying if on top of this, so if I zoom in way in here, and I have, this is a situation we have. We have a 800 millivolt DC voltage right here. And on top of it, we have this microphone that's got a signal with 1 millivolt of, signal that we're interested in. The 800 millivolt doesn't give us any information. That's just to bias this gain stage, this amplifier stage. The information is what this microphone is outputting. And that's just going to be a 1 millivolt signal on top of this. So if I was going to look at the input, let me just draw what the base voltage would look like with time. So the voltage on the base, what would it look like? It would be centered around 800 millivolts. And then from the microphone, you'd be getting signals, as I'm talking or whatever, of 1 millivolt around that. And that's the signal I want to amplify. I don't care about the 800 millivolts. It's just 800 millivolts is purely put there to get your amplifier in the right state so it can gain up this 1 millivolt signal. So what it looks like if we look at the VBE versus IC curve is it looks like we've got this really, if I was going to draw this sort of like this would be, I don't know, time here. It looks like I got just a real small signal here of 1 millivolt. And that 1 millivolt signal is causing a change in my output current. So that 1 millivolt signal is giving me some change in collector current. And if I run that change, if this delta IC runs across this resistive, the R sub C of 100, that gives me some delta IC R sub C. So it gives me an output voltage change that only is the signal I'm interested in. Okay. And basically that puts us, all the 800 millivolts is doing is putting us in this happy place in the curve where we're going to, for just 1 millivolt of signal, hopefully we're going to get a higher amount of voltage swing at the output. Okay, so we're moving this around, and then this is changing out, and this is also what the small signal model means. Okay, so with the large signal model, we calculated in exercise example 4.10, we calculated that we're at 6.92 milliamps. Now all we have to do is, with this small signal model, multiply this by the GM and get the change in voltage. So because, let's see, delta, so what happens is delta I sub C is equal to G sub M V sub pi. Okay, G sub M is I sub C over VT. So it's 6.92 milliamps over 26 millivolts. Okay, so I put that all in here. I'll get the delta I sub C is 266 microamps. So this variation is going to be 266 microamps. And if I want to look at the change in the output voltage.
Professor, sorry to interrupt you, but is the
Sure.
V sub pi the 1 millivolt?
The V sub pi is the 1 millivolt. That's correct. And so this change in output voltage is just a change in the collector current times the collector resistor, and that's 266 microamps times 100, which is equal to 26.7 millivolts. Okay, so what that means is this circuit, it took a millivolt signal on its input and multiplied it by 26 times, or a gain of 26, to have it on its output. So if I was just going to look at the, it's hard to draw here to have it really in, whoops, sorry guys. I lost my notebook. So if I was going to draw something like this, it would be, again, it's hard to draw because I didn't scale this too well, but it would basically give you a huge swing from this output. So it takes that input and multiplies it by 26. So gain of 26.7 times. Okay, and that's the magic of the transistor. That's where all of this has been getting to, is we can use this device to just take a very small signal, like again from your microphone, and amplify it to a level where you can drive a speaker or RF amplifier or whatever. Okay.
I have a question.
Sure.
How does the VE affect the output? Like, do we want to have it at 8 millivolts or lower than that, greater than that? Like, what's the optimal?
Well, so
output?
Sure. So the answer to that is it's going to be a very complicated answer. but it's worth trying to give you an answer. So let me give it a try. So let me just redraw this thing so we can play with it. So generally, so I sub c is I sub s exponential of VBE over VT. Means that, that's the curve we have. Okay, so generally what happens as you increase VBE, you are walking up this curve, right? So increasing, whoops, let me just put it. VBE. So for example, if we increase, if you guys remember, we came up with this a while back and it drops out of the equation, but if we increase VBE by only 60 millivolts, I sub c goes up by a factor of 10, okay, because it's exponential. So as we increase VBE, we get a significantly higher current. Okay, so what does that mean? Well, so you're operating at higher and higher slope region. So we would go from, say, operating here to operating up here. So you're going from a slope to a higher slope. Means your gain is going up. You can see that from your GM. So remember, the gain is minus GM R out, or R sub C in this case. So the higher the GM, the higher the gain. So the GM equation is I sub C over VT. And so if we increase VBE by, it goes up by just 60 millivolts, which isn't much. I sub C goes up by a factor of 10. And that means that the gain also goes up by a factor of 10. So from that point of view, you just want to crank up that VBE and get, there's usually no such thing as too much gain. You want to get, so that tells you, oh yeah, I just crank up my VBE, crank up the collector current, and I get a higher gain from that point of view. Do you follow that so far, Epsilon?
Yeah, so at this point, we pretty much have to just look at the limitation of the speaker, correct?
Well, yeah, but even before that, though, the other important thing is power consumption. So I've been telling you guys, one of it is the speaker, like you're saying, but before that, you are limited either because you're battery powered or heat reasons or whatever. Power is always at a premium. So look at how the power changes. So the power is equal to I times V. If you look at the power that our circuit draws from BCE. Okay, this is I. So we multiply I times V and we get that power. Okay, so as we increase the current, so let's say our current goes up by a factor of 10. So now we got 10 times the original power of what we had in our previous VBE. And because we've increased I sub C, remember we have to keep this point from dropping too low. This point, or output, or the collector, is VCE minus I sub C R sub C. So if we keep R sub C the same, we've cranked up I sub C by a factor of 10, means that this point, if we want to keep that point from being higher than VBE to keep this in forward active, so we have to increase increase VCE. So whatever that is, I don't know. It depends on where you start, depends on R sub E. So it'll be some X factor times the voltage. So the power significantly goes up. It's going up by a factor of like 20, 30 as you're increasing your gain by these big factors. And if you do that in every circuit in your system, your power budget goes to hell. So even before anything else, you're going to be limited by the power consumption of your circuit. And then, like you said, if you have too much gain, you could end up clipping your signal, clipping your speaker system, etc. So other results could happen also. Did that make sense?
Yeah, it's actually pretty interesting.
Yeah. There's nothing for free in engineering. Almost. So,
thank you.
Okay, sure. It was a very good question, actually. I think it helped us take a look at this.
It's like a little intro for power class.
Yeah, there you go. No, I don't know anything about that stuff. I just assume you're correct.
Yeah.
Okay, so that's where, and in fact, okay, like it's actually also a good entree into the next example, which is example 4.12. Okay, so now we're again referring back to example 4.11. So what we had there was this guy, 800 millivolts. And I think this was 1.8 volts VCE, and R sub C is equal to 100. So what this example is asking us for is what happens if we, so R sub C, change that to 200 ohms and change VCE to 3.6 volts. It's asking us if we do both of those, are we still forward bias? Okay, so let's look at it. So when we do those two things, so when we change R sub C and VCE, we haven't changed the VBE at all. So assuming that the answer is yes, and we're still in forward active mode, I sub C doesn't change, because remember, I sub C is just a function of VBE. Okay, so I sub C is not going to change. So I sub C is going to stay the same as example 4.11. It's going to stay at 6.92 milliamps. Okay, so if we increase R equal to 200, so we use it to figure out this voltage X, is what we're trying to do, and make sure it stays higher than 800 millivolts, because again, we haven't changed the VBE at all. So when we look at V of X is VCE, so let's call this VCE2. VCE2 is equal to that, minus I sub C, and let's call this RC2. So 3.6 volts minus 6.92 times 10 to the minus 3 times 200. And that comes out to so what is that? It's 3.6 minus 1.384 volts, 2.216 volts. Okay, so that's great. 2.216 is higher than 800 millivolts, 2.216 volts. So So if we do both of those things, we are still in forward active mode. Okay. But let's look at what would happen if VCE had stayed at 1.8. So what if VCE had stayed at 1.8 volts? Then V sub X would have been VCE1 minus I sub C RC2, or 1.8 volts minus 6.92 milliamps times 200 ohms, or 1.8 volts minus 1.384 volts, and it would have been 0.416 volts.
So it's no longer forward active?
It's no longer forward active because it's lower than the base voltage. So you see how, in an effort to increase the gain, so notice here, I didn't change the I sub C, so the transconductance here stayed the same. GM stays the same as before, but the equation for the gain is transconductance GM times the R here. So if I increase the R by a factor of 2 and don't touch the gain. In fact, let me write it out for you. So G sub M, G sub M is I sub C over VT. So that didn't change. I think that was, what was that? That was 0.266 1 over ohm. Okay, so the gain, the change in V out is that 0.266 1 over ohm times 200. So now that value ends up being 53.4 millivolts, or our gain is now 53.4x. So remember, in 4.11, our gain was half that amount, because the gain, we didn't change the current, so we didn't change the transconductance, we just doubled the resistance, and we doubled our gain. But if we hadn't been careful, if we hadn't increased this VCE, we would have screwed ourselves up and gotten ourselves out of the forward active mode, and the circuit wouldn't have worked like we were hoping it was going to work. So that's like a good example here. And as soon as we took that VCE, we doubled VCE. That means the power consumption here, again, is I times V, which we kept the I the same. We doubled the voltage, so we doubled the power consumption to get that doubling in gain. Okay? Everybody, any questions about that? Okay, so let's see.
Actually, I do. So when you calculated delta V out, you did the GM times the RC, right? And that was the gain, or is that the delta V out? And then, or
so that's the delta. So okay, so good question. So thanks. I was skipping a couple. I was skipping not a couple of steps, but one step. So the gain is delta V out over delta V in. Okay, so the delta V out is 53 millivolts, and just because the guy making this example was being nice to us, he'd made delta V in 1 millivolt. So it ends up being, the gain ends up being 53.4. Okay, but strictly speaking, like you're pointing out, is the gain is the change in output voltage over the change in the input voltage. And I just kind of skipped that.
Thank you. I really appreciate that. Thank you.
Sure. Okay, so I think that's where we are with let's just call all that first order effects of the NPN bipolar transistor. So we've got the transistor, we figured out the large signal model. And again, what the large signal model does is it tells you where you are, tells you where you are on this curve. That's what for the large signal model. And then we got the small signal model, which was giving us, a linear approximation around where we are. So the calculation for the gain is going to be easy. So, we just end up making the voltage gain GM times R. Okay, so that's what we have so far. So those are what I call first order effects. So now, with the transistor does have second order effects, and there is one in particular that we'll talk about that's relatively important, and that's called the early effect. And the word early here is just the name of the guy who came up with this effect or modeled the effect. I don't know. It doesn't mean anything is earlier than anything else. It's just an effect. And it's a second order effect that affects the gain of your circuit. Okay. So just as a reminder about the full equation of the collector current. So we tend to draw it as I sub C is I sub S exponential of VBE over VT. But remember, it was really this I sub S exponential of VBE over VT minus 1. And we write it in this simplified form just because exponential of VBE over VT. Just because exponential of VBE over VT, if we bias it when it's much greater than 1, we can just use the simplified equation. And also I sub S is sort of a short for a whole bunch of other stuff, which I'm going to all write it all up for you here. And we had these earlier when we started. So that's just area of the emitter times charge of the electron, diffusion constant, intrinsic carrier concentration squared over. And so don't worry too much about this stuff. I'm just going to tell you guys about what's important. This is a long way to get to a point. Okay, so that's the full equation for I sub C. And we'd seen this earlier. So now one thing we've done, one thing that's implicit in this circuit is that the base width, okay, this is the base width, W sub B, stays constant. Okay, and as a first order, it does stay constant. Okay, and what that does is that means that if we look at VCE versus I sub C plots, we said as long as we stay, above, as long as we keep the collector base junction reverse bias, this is just a flat curve. These are just straight flat curves. And there's no change in I sub C with a change in VCE. Okay, so that's like a first order view of this. But that's, strictly speaking, that's not completely correct. Okay, so what really happens, let me just first jump to the punchline here. What really happens is there is a slight slope, a slight change in collector current with VCE. So there is a dependence of I sub C with VCE. That's what you see in real bipolar transistors. And the reason for it is that as VCE changes, as VCE increases, our base width actually shrinks. Okay, the size of this thing goes down. And let's take a look at why that is. So if we draw the NPN, like that. So this is N plus P N. This guy is our VCE. So this is guy's the collector. This is the base. So it's going to get VBE. And this guy's the emitter. Okay. So let's say, we have a certain voltage VCE1. And if you guys remember again, so this junction is forward biased and this junction is reverse bias. And if this junction is reverse bias, it means that it has a certain depletion region around this junction. And what was happening was electrons would get, so if I was going to draw the concentration of electrons in the base, so let's say this axis is electron concentration. It would be high in the emitter size of the base, and it would go to 0 in the collector size, because all the electrons would get pulled into the base, into the collector, I'm sorry. Okay. Now let's say what happens if we have the same device. This would probably be a really bad idea to be this lazy, but what the heck. So you take the same guy and you change VCE. So, whoops. You give it another VCE. So let's call it VCE2. And let's say VCE2 is much bigger than VCE1. What happens? Okay, so what happens is, whoops, as you increase the reverse bias, so higher VCE increases the reverse bias from the collector to the base, and it increases the width of the depletion region. So just to draw an extreme case, so instead of the depletion region being just this wide, it can get wider. And that means the electrons have to go to 0. That gradient of electrons is actually a lot higher. That means my collector current is higher. Another simple way to look at it is just that the width of the base, in this case, there was a width of the base 1, and here we have a width, so this was the, oops, let me just get another color. So here was this width of the base, so WB1, and we have another base width here, WB2, and WB1 is bigger than WB2. Means that, if you look back on this equation, if you have a smaller WB, the current goes up. So the effective, that's really how I look at it, is that the effective width of the base decreases as the collector base junction gets into more and more reverse bias. Okay, so as I drew earlier, what happens is if we look at the collector emitter versus I sub C curves, so instead of just being constant up to a certain point, before, while you're still forward active. What really happens is the current goes up because of this early effect. And this is without early effect. Okay, so this complicates our life a little bit. And what we have to do is we have to change our I sub c equation. Again, our I sub c is was initially without early effect. Without early effect. I sub c is exponential of VBE over VT. And well, let's just draw, yeah, exponential of VBE over VT. And there was, so this has no dependence on VCE. So if you do the same equation with early effect, with considering the early effect, we'd end up with exponential of VBE over V sub t times 1 plus VCE over V sub A. And this V sub A is the so-called early voltage. And the higher this early voltage, the shallower the curve. So if let's say if we had a very high early voltage, it would kind of looks like this. High V sub A, lower V sub A. So what you'll see in a lot of the homework examples is it says, okay, assume V sub A is infinity. If you make V sub A infinity, that means you're not considering the early voltage, or the device is so well designed that this early voltage effect isn't very important. Because if you do that, you make V sub A is equal to infinity, this term drops to 0, and we just get our original term. And as the early voltage decreases, you'll see things like maybe 20 volts or whatever, 10, 20 volts. This term ends up being noticeable. Although it's never, it's not like it's going to get to a value of 1. It's not going to double your current, but it might go up to like, I don't know, maybe like, increase your current by 10% or something like that. So compared to where you'd be here, you might be 10% higher, that kind of thing. Okay, so any questions about that? So the early effect is this, the reason we get it is because of this depletion region increase as a function of the collector voltage, the collector base voltage going up. And what that does is it creates a dependency now between the collector current and the collector emitter voltage that we would have to consider if the early voltage is low enough. Okay, so any questions about that? Okay, so let's do an example, take a look at it. And a lot, so like if you buy, again, if you're buying a bipolar transistor or whatever, the spec sheet is going to tell you what this V sub A is. It'll give you a number, 100 volts, 20 volts, whatever it is, sort of like beta and I sub S. Okay, so example 4.3, 4.13, sorry. So it says, I sub C is 1 milliamp with V sub CE of 2 volts. And it wants us to calculate VBE. in two cases, with V sub A being infinity or V sub A being 20 volts. And it's telling us I sub S. Okay, so let's see. So let's start first with if V sub A is equal to infinity. So again, the equation we have is now the new equation. This is a large signal equation, exponential of VBE over VT times 1 plus VCE over V sub A. Okay, so when the early voltage is infinite, we can just ignore this term here. So we get our original equation for I sub C. So we would end up with just I sub C is I sub S exponential of VBE over VT. And then we can move things around to get VBE, ends up being V sub T natural log of IC over I sub S. And, we can throw in all the numbers. Natural log of 1 milliamp over 2 times 10 to the minus 16 amps. And that's equal to 760 millivolts. Okay, so that's with a very high early voltage, or basically no, well, how should I put this? No early effect, let's say. Okay, so now what if V sub A is 20 volts? Now we do have to put it in part of our equation. So I sub C is, now we have to use, oops. We can't ignore this guy, the second term. Sorry guys, give me 1 second. Let me see if I can close down the door here. Okay. So here now VB gets a little bit more complicated. Is V sub T, I'm just reordering the equation. Sorry guys. Let me rewrite this. Okay, so we're just keeping that sort of second term in our VB equations, VBE. And so now with all this and V sub A being 20 volts, we end up with 758 millivolts. So as you can see, I sub C really didn't change that much with or without the early effect when we're talking about 20 volts, early effect of 20 volts versus early effect of infinity. Okay? So from this point of view, early effect doesn't seem like much of a big deal, but just let's keep peeling this onion and you'll see where it starts giving you a problem. Okay, it really starts giving us a problem during small signal analysis. So it kind of starts messing with our gain. Okay, so again, the large signal with the early voltage is just let me rewrite this. So large, whoops. with the early voltage. So I sub C is I sub S exponential of VBE over VT. That guy changes, 1 plus VCE over V sub A. I sub B really doesn't change. It's just 1 over beta I sub S exponential of VBE over VT. And I sub E stays I sub B plus I sub C. So basically the change we get is only to I sub C as part of this early voltage. Okay, so because of that, when we look at small signal, by the way, remember when we started calculating small signal, what we said is if you had whatever 3-port network, the way we would come up with the small signal model is we would go through each port, we would sort of short the other ports to 0, and then we would sort of modulate, look at the change in all the currents with the change into the voltage of that particular terminal only. And fortunately, when there was no discussion of early voltage, we're just looking at the bipolar transistor without it. The only effect we had was, VBE was the only thing that mattered because, if you tweak the emitter voltage or the collector voltage, the current wasn't changing because remember GM was a change in, or not GM, sorry, but we're looking for changes in, I totally kill this. We're looking for changes in voltage causing changes in current. And it turned out without the early voltage, the only thing that mattered was VBE. And that was represented by GM was, and I still screwed this up, we're looking for changes in current with changes in voltage. Okay, and so the only thing that mattered at that point was VBE. And there was a change in the collector current with the change in the VBE. And we call that transconductance. And that even with the early voltage, this stays the same. So G sub M stays G sub M stays I sub C over VT, even with the early voltage. G sub M is I sub C over V sub T. Okay, and then we had this resistance value that was modeling the base emitter diode, and that was beta, or we represent that as a resistor, R sub pi. That was beta over G sub M, or beta times V sub T over I sub C, and that still stays the same. But when we look at the output, then we change the collector voltage now, we do get a change in current. So if we do an equation of delta VCE, delta I sub C, and I'm just gonna, because we have an equation for I sub C, I'm gonna rewrite that as d I sub C over d VCE that's equal to 1 over I sub S over V sub A exponential of VBE over VT. Okay, so when you look at, so V is equal to IR, and if you're looking at this change with respect to current, we're looking at a resistance. So we call that R out or R0, really R out is just this value. It's V sub A over I sub s exponential of VBE over VT, or V sub A over I sub C. This term is just equal to I sub C. Okay, so if we was going to redraw the small signal model, the input would still look the same from the base side. We would have a resistor R sub I, and we call the voltage across it V sub pi. Still be connected to the emitter. And we still have a transconductance, current source with the value G sub M V sub pi. And then the only change is now, because of the early effect, we have the transistor itself is going to have an output resistance that's equal to V sub A over I sub C. Okay, any questions about that? No,
This is for the small signal, correct?
I'm sorry?
This is for the small signal?
This is just for the small signal, yeah.
Okay, thank you.
Okay, and sort of like the punchline is coming about why, we looked at the early effect for the large signal. We calculated it up here. The change when we considered an early voltage and its effect on the large signal, it didn't really do very much. It just changed our, this is a minor change in VBE, et cetera. It wasn't a very big deal. But let's take a look at the same thing with small signal. And let's see what these are, what it does. So if, let's say example 4.14, it says transistor has I sub C of 1 milliamp, a beta of 100, and an early voltage of 15 volts. What's the small signal model? We said the GM stays the same. It's I sub C over VT. So it's 1 milliamp over 26 millivolts. 1 over 26 ohms. And R sub pi stays the same. And that's 2,600 ohms. But now we end up with an output resistance as well. R sub O is V sub A over I sub C. Okay, V sub A is 15 volts over 1 milliamp. And so that is equal to 15 kilo ohm. Okay. Cool. So now let's think of it now. What does this 15 kilo ohm mean? Remember when we talked about having, how do we get higher gain out of this simple bipolar stage? We said one thing we can do is we can keep increasing this external resistor, this R sub C. We can keep increasing, R sub C for higher gain. But you see, so let me just draw the small signal model again. And and then just focus on the RO. And then if we have an R sub C, an external R sub C, it goes in parallel with the R sub O. And the effect is that, in this case, let's say R sub O is 15 kilo ohms. So that ends up being in parallel with R sub C. So as the R sub C value, when R sub C value is low, let's say R sub C was 100 ohms, our total output resistance would still be close to 100 ohms because it's in parallel with a 15 kilo ohm. But let's say you keep increasing R sub C, trying to increase the gain, and imagine if you try to increase R sub C to 15 kilo ohms. You're expecting a certain gain. You're expecting your transconductance times 15 kilo ohms, but the transistor itself has a resistance of 15 kilo ohms in parallel with it. So the effective resistance in total is only half of what you expect at that point. It's only 7.5 kilo ohms. So basically the early voltage, what it does is it sets a limit to how much gain you can get from a single bipolar transistor stage. We said you could increase the supply voltage and all this kind of stuff, but there will be a limit which comes from just your own output resistance. Okay, so it really, I think the big effect of the early voltage has to do with the small signal gain, and it does tend to limit the maximum small signal gain you can get out of a bipolar transistor. Any questions about that? That pretty much, as far as we're concerned now, puts us, at the end of the NPN bipolar transistor. We have, let's see, do I want to say anything about, how are we doing on time? I think I'm going to skip saturation. So what happens is, well, I'll just maybe describe saturation a little bit. So when we're talking about the VCE versus I sub C curves, we keep coming to this place and we're saying, well, as long as VCE doesn't drop below a certain level, it's flat. Or, even if we include the early voltage, it's, has some early voltage. But, so what happens here? So here we're in forward active mode. And here we're not on this side of the curve, on the left side of the curve. We're not in forward active mode. And this region is a region called saturation for various reasons. But basically what the curve looks like, it is your I sub C becomes a very strong function of VCE. And so you're no longer a current source. You're no longer a voltage controlled current source here. You're something like a bad resistor or something like that, because you no longer have a high output impedance. You have a low output impedance. And I think the only thing I want to say about saturation is it's just, barring some old logic families from like 30 years ago, it's just a bad place to be, and just don't go there. I just wanted to give you guys the name of this region of operation, saturation. So if you hear it later on, you kind of recognize what it means. It means that you're no longer in a region where you can get gain from your bipolar transistor or significant gain from your bipolar transistor, because you're no longer acting as a voltage controlled current source. Okay, so I'm just going to leave it at that. Yeah, go ahead.
So after we get into out of saturation into forward active mode, is there a point where we can get back into, like, if we're not careful, we get back into saturation? Or the circuit will still, like, will just stay at forward active mode once it's there.
Can you ask the question again? Sorry.
Yeah, of course. So like so before getting into forward active mode, we're like in the original saturation, correct?
So you have your circuit, your VCE is low, and you're just slowly increasing VCE,
Correct.
and initially in saturation, then you get in a forward active mode.
Oh, okay. So if once we are into active mode, forward
Yeah.
active mode, if we decrease, what's it, VEE?
VCE.
Which
or
VCE?
Yeah,
If we decrease VCE, we get back into saturation, correct?
that's correct. Yeah.
All right, cool.
And
Right,
so
thank you.
yeah, and it's not like a destructive effect. You're just biasing it in this bad state where it's no longer acting like a voltage controlled current source.
So we control, right? Like whether we are in saturation or not. Like the circuit would not go by itself into it.
It will not. Yeah, you're in control.
Okay.
You are in control of the bias conditions, in other words, of your circuit.
Awesome.
So as long as you operate the circuit with the right bias conditions, it will be, doing the correct thing.
Thank you.
Sure. Okay, so sorry, guys, I'm gonna kind of finish up this bipolar transistor, and we can move to more bipolar transistor circuits. So let me just briefly touch on one more thing. So I think we've covered NPN, small signal, large signal, early voltage, saturation, and just want to touch on another type of transistor again because you guys will hear about it, and that's called a PNP. Early on, we said it's also possible to get a bipolar transistor if I inverted everything. So if I had a P plus NP transistor, I could still get this to work like a bipolar transistor, except that now the currents going from the emitter to the collector it'd be a hole current as opposed to an electron current. And the current going into the base, so it'd still be, collector, base, emitter. The current on the base, it would be an electron current going in here. So it would have the same bipolar action, except everything's inverted. So basically the currents are going in the opposite direction, and as it turns out, your voltages also, because notice that you still want the same thing. You still want this PN junction, the base emitter, to be forward bias. But notice the emitter is now, this is like a kind of a brain teaser or mind bender or what you want to talk about, because everything is reversed. Now the emitter is P plus and the base is N. So to make this junction forward bias, you have to make the base lower than the emitter. Okay, so if I draw this thing, like this, and because of the PNP, notice the direction, the way they signifies PNP is this arrow always goes on the emitter side, but instead of the arrow pointing out, the arrow is now pointing in to signify that it's PNP. And so what we do is we invert our battery between base and emitter. So the VBE makes the emitter lower than the base by 800 millivolts. Again, that's because that junction is a P plus N junction as opposed to an N plus P junction. And then same thing with the VCE. Just makes my head hurt to look at it like this. VCE plus and minus. Okay. And so we're not going to do a lot of PNP again. I just wanted you guys to be familiar with the concept. the way you actually tend to use it is actually sort of this flipped around. And so the way you use it is you actually put the emitter on top. So let's say your highest voltage was VCC or VCC, okay? So, and then you connect a voltage here, VBE. So I just basically what I did is I flipped the emitter up here and the collector down here. So here's the emitter and here's the collector. So this voltage VBE is still keeping the base lower than the emitter to forward bias this junction. And it's also basically making the base higher than the collector to make this junction reverse bias. And the total I sub C looks like that. I sub E looks like that. And I sub B goes in. And then, from a large signal point of view, everything is inverted. So I sub C is I sub S exponential of VEB over VT. So this tells you want to have the emitter higher than the base to get the collector current. And I sub B is I sub S over beta exponential of VBE over VT. I sub E equals to beta plus 1 over beta exponential of VEB over VT.
What does VEB stand for? Is it the same as VBE or?
It's the reverse. So it's the emitter base voltage versus the base emitter voltage.
Okay.
So the base emitter voltage is a positive value if the base is larger. So VBE is VB minus VE. So it's a positive value if the base is higher than the emitter. And VEB is V emitter minus V base. So it's a positive value if the emitter is higher than the base.
So, Professor, the sign is switched, right?
The sign, basically you have to kind of like flip this thing and get the base to be a lower voltage than the emitter and the base to be a higher voltage than the collector. If you remember, that's completely the opposite of NPN to get this thing into forward active.
Yeah.
So everything's flipped around. And like I said, it makes my head hurt. You'll probably might see examples of it. I'm not going to go into it too much. It's usually used as like a load for gain stages, et cetera, or current mirrors, which you guys aren't familiar with. So it is used, but we're not going to see a lot of it in this class. I just wanted to make sure you guys had heard of it.
Professor, just a question. So the NPN transistor, the I of emitter was IB plus IC, right? So, but in this case with the PNP, the inversion is beta plus 1 over beta.
Yeah, but it still ends up being the same. I just wrote it, in a funny way, but it's still the same. It's still I sub B plus I sub C.
Okay.
I just sort of wrote it up in longhand, I guess.
Okay, thank you very much.
Sure. Okay, guys. So I'm going to stop here. So this now we're ending chapter 4, and starting Tuesday we're going to go to chapter 5, which is more sort of circuits to do with bipolar transistor. So I think now we're getting ready. You guessed it, our quiz 3. But because I haven't posted the answers for the homework yet, so which I'm going to do this weekend, we'll have the quiz not next week, but the week after. So that'll be November, is it 14th, 15th, 17th. Okay, I'll put that up on Blackboard. So it'll give you guys some time to get the answers to the homework and be able to absorb them.
Thank you.
Professor, speaking of the homework, on what section on Blackboard is it? Because I was going through the quiz assignments and I didn't see it after the second homework solution.
Where is it? Let me see. Just give me 1 second, guys. Let's see, did I have in my announcements? Oh, sorry. I think I called it the wrong thing. Did I? It's under course content, and I think it's called the wrong thing. It says homework number 2 problems. It should be called homework number 3 problems, I believe. So I'll change that right now. I don't know if you're online, you can take a look at it.
Because I'm on the what is it? Yeah, I'm on course content, and all I can say is quiz 2, and then homework number 2 problems.
Yeah, so that should be called homework number 3
I
problems.
see.
Yeah,
Got it.
I did that wrong, so I'll just change that name to homework 3 problems.
Yeah, I only looked at the title, and then I was like, oh no, I should have seen the numbers.
Nope, no, I shouldn't have put it wrong.
Thank you, Professor. Also, I have another question, but I would like to ask it like privately, like if you don't mind.
Sure. The best way to do it is if you could email me, or if you want to come to the office hours tomorrow, or dial in.
Office hours tomorrow? What time?
4 p.m. tomorrow. There's
4
like
p.m.
a Zoom invite.
Okay, but it's the same Zoom address, right? I
think it's a different one. It should be in the announcements, I think.
Yeah, it's a separate link.
But is it on the announcements? So I can find it later.
Where is it?
Announcements.
Network is.
Oh, I found it. Yeah, it says Zoom office hours.
Yeah.
Got it. Okay, Professor.
Okay. So I'll talk to you tomorrow then.
Yeah, sounds good.
Okay,
Thank you.
thanks.
Have a good one.
Thanks. You too. Bye.
Bye.
Thank you, Professor. Have a good one. Bye-bye.
Thank you. Take care. Bye.
Oh, Professor?
Yeah.
So, I mean, these past few weeks have been pretty busy for me. So, I think I might have more time this weekend to attempt the problems. So, I think I can probably go to office hours on Monday. And we can catch up on then. But I don't think I'll have anything done by Friday.
Okay. That's fine. No worries.
All right. Sounds good. Thank you. Have a good weekend.
You too. Take care. Bye.